Hello, 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 everybody. So good to see everyone today for office hour number, what is it, 14, 15 of World Quant University's course in machine learning, unit numero dos, unit 2. Anyways, how is everybody doing? If we're meeting for the first time, hello, my name is Nicholas, but I'm guessing that a lot of you already know me. In fact, I see Innocent and Arthur here in the chat. How are both of you doing? Florence here. They say they feel great. I'm glad. I'm hoping you're recovering from your cold. Stefan is also here. Welcome, Stefan. Good to see you. Mohammed Drebo is here as well. This is great. So good to see everyone again. You guys are really the core of the course. Mohammed saying Hakuna Matata. I love it. Same to you. I see John from Sierra Leone is here. Welcome. Dimitra's also here. Glad you could make it. So let's pull up the old board here. What are you guys interested in talking about today? One thing we should probably talk about is the NLP mini project, since we're in week 4, or just NLP in general. If people have NLP questions, what else would you guys like to look at today? What are we interested in focusing on? Just some general NLP. NLP in other languages, we can definitely look at that. And Arthur's interested in the mini project. Of course, we'll definitely look at that as well. Dimitri wants to know about Mongo to pandas. I feel like that's a little bit outside the scope of this course. So I agree with your LOL. I think we're not going to quite do that today. Florin is absolutely right that the human brain is very good at natural language processing because language is kind of our thing. Let me see if I can find some information. Well, let's begin talking a little bit about NLP in general. I like that idea. So let's do the following. I'm going to open up data course and then machine learning, and I'll open up natural language processing. And before I do that, or rather before I get too set in my ways, just let me see if I can find a file that I used previously, which might be helpful for us. Let me organize this by name. All right, well, we'll work from a blank template. So I'm going to pull up my notebook here, and previously, let's think about how we made models previously, and then let's think about how natural language processing adds a step to our original pipeline and what it is we need to do to make sure that our models can work with human language. So the first thing we should do is let's think about our regular models. We usually have a feature matrix, which we call big X, and we usually have some labels, which we call little y, and we use this information to train our model. And our model usually has, I don't know, some sort of transformer, and then it has a predictor, and that's how it works. And we probably take this whole predictor and transformer and we put it into a pipeline. Now, my question for you guys is, what in our feature matrix, what up until now has been in our feature matrix? So Demetrius says it's been some sort of data set, but let's be more specific. What does that data set consist of? Joebo says features. Up until now, in the things we've done previously, we've generally had, and Mohammed is saying it, we've had numbers in our feature matrix, right? Ones and zeros and point numbers and integers and all that stuff. And the reason is because the models that we are building, they depend on numbers as features in order to create a model. So we have numeric data, as Innocent is rightly saying. And there have been times when we've had textual data in the form of like categorical features, like, small, medium, large, or state in the US, Alaska, Ohio, I don't know, Washington. And when we had those textual features, we did something called one-hot encoding, where we turned those pieces of text, which happen to symbolize categorical features, and we turn them into numerical features, ones and zeros, that we could then put into our model. So we've been using numerical input up until now, and now all of a sudden, when natural language processing comes along, that's going to change because we no longer have numbers, right? We now have text. And the question is, how do I turn a line of text into a row of numbers that I can include as an observation in a feature matrix? How can I do some feature engineering to turn text into something that my model will understand? So what I'm going to do now is I'm going to open up a new notebook. And I'm going to create just one document. And I'll say that document is the fox jumped over the moon. And in order for me to, let's say this is just one sentence, when we're talking about NLP, if we're talking about one observation, we call it a document. In this case, the document just happens to be one sentence. But what I need to do is I need to turn this into something that is understandable to a model. So, and this is before we get to, sorry, I forgot to share my screen. So I have the fox jumped over the moon, and I'm saving it as a doc. And before we get to tenses and lemmatization and all of that stuff, this is what we're dealing with here. Text that we need to turn into words, excuse me, that we need to turn into numerical features. So let's start with one way of doing that, which is probably sort of the baseline way of doing it. And it's called the bag of words, or BOW model. And what I'm going to do is I'm going to go from sklearn.featureExtraction.text import count vectorizer. And I'm also going to make this lowercase the, just so we don't have any problems here. And what I'm going to do is I'm going to call this my BOW BOVEC. So this is my bag of words vectorizer. And I'll instantiate my count vectorizer. And then next I will train it. I'll fit it using the doc. And actually, I think this needs to be a list with one document in it. And then I'm going to say my word counts equals my BOVEC, and I'll transform my doc. And then I'm going to print my word counts. And actually, I'm going to do sparse equals false. Oh, whoops, hold on. Let me get my count vectorizer. Give me 1 second, guys. Count sklearn count vectorizer. So I'll do a few things here. I will have my count vectorizer, and I'll have it lowercase equals true. And what I have here is I have, well, let's look at the type. So this is a sparse matrix. So actually, maybe what I could do is go word counts to array. There we go. And what I'm going to do is next go, I'm going to import pandas just so that we can see everything. So I'm going to import pandas as PD. And then next I'm going to go df data frame equals PD. And then I will add my word counts to array. And the columns will equal my bovec dot vocabulary. And then from there, I'll look at df. This is a little bit wrong. Actually, I'm going to do this as sorted. There we go. Okay, so here's one way in which I can represent my words as features in a feature matrix. I can do a word count for each. So each row will be one sentence, and each column will be whether or not a given word appeared in that document. So in this case, the appeared twice because we had the fox jumped over the moon. And so here we'll have the appeared twice. And I can also say, I can create a second document. So I could go, the fox jumped over the moon, and I can say, the moon was full that night. And I can add another one. The night was cold. So here I have 3 sentences. And what I can do is I can then convert them into features by just looking at where they or how often they appear in a given sentence or in a given document. In this case, we're using sentences as documents. So here I have all the words that appear in all of my sentences. And in each observation, I'll have the count. There'll be a 1 if a given word appeared, or there'll be a 2 if it appeared more than once. And if it didn't appear at all, there'll be a 0. And so this is one way in which I can turn textual data into numerical data that I can then feed into a model. Now, I see some of you have some questions, and I see Florin has some questions especially. Is grammar important? This is a question for you guys. Is grammar important in this technique? Does it matter that cold is an adjective and fox is a noun? Or that was is a verb and that verb is in the past tense? I see Florin has a question. Florin wants to know, how will we distinguish between the sentence, the girl is a dog, and the dog is a girl? So I'm going to copy and paste those in there. And I'll train it again. And if I look at our last two sentences, the girl is a dog and the dog is a girl, they are identical in terms of their features. So, for example, word order doesn't matter here. And like Muhammad said, grammar also doesn't matter here. And Stefan is right, it's a little bit like a set. And also, language doesn't matter here either. I could write this in English. I could write it in Spanish, you know? And again, it doesn't matter. And I could do this also in German. I could say, Das Machten ist ein Hund. Again, it doesn't matter whether I say Das Machten ist ein Hund or Der Hund ist ein Machten. All it's seeing, this our computer is not reading the language as language, right? It's reading it as strings. And all it's doing is it's saying, if this string appears, count it. If this word appears, these this series of characters with a space on either side appears, mark it. And this can be very useful, right? If I am building a model that'll characterize reviews on Amazon, and I want to categorize either reviews as positive or negative, there's some words that if they come up a lot and over again, there'll be an indication that it's a negative review, right? Terrible, this is an awful product. And so over a large corpus, over a big data set, those word counts can be very helpful. But what's important to remember about the bag of words model is it doesn't care about language, it doesn't care about word order, it doesn't care about grammar. It's not reading the words the way that you and I read the words. It's just interested in word count. If we've talked about the count vectorizer, the other thing we need to talk about is the hashing vectorizer. And the hashing vectorizer works very similarly. And Innocent is raising a great point. If a typo would be considered another word, that's absolutely right. A typo would be considered another word. And that's why a lot of natural language processing is about cleaning texts at this level. So I'm going to import another vectorizer. And by the way, that's what a vectorizer is. A vectorizer is a transformer that will take text and turn it into numerical features that you can then pump into your model. Now, let me let me before I see your question, Florin, and I will get to it, but I want to talk about the hashing vectorizer first. And I'm going to call this my hash vec. And I'm also going to pull up the hashing vectorizer here, sklearn hashing vectorizer. And I'll copy and paste this into our chat for those who are interested in it. So I'm going to have a hashing vectorizer, and I'm going to train it on the same corpus we had before. Right now, our corpus is still just these two German phrases. Let's turn them back into English just so I don't get confused because I don't actually speak German. So I'll say the man is a dog and the dog is a man. Now, a hashing vectorizer works a little bit differently. So next I'm going to go to word counts. Uh, Somebody is asking about it's not recognizing the character A, and I suspect that's because we have, uh, let me just look at the documentation. Yeah, I'm not sure why this is not picking up A, but let's not worry about that too much right now. And Vladimir is right. I'm not using very meaningful phrases, but I'm trying to keep it simple. Let's use Charles Dickens. How about it was the best of times, it was the worst of times. So what I'll do is I'm going to take, let's see here, sparse equals false. Actually, I'll keep that like this, and then I'll also look at hashing vectorizer. I'm going to do stop words, n-gram range, analyzer, number of features. Okay, number of features equals 20. And then I'm going to do word counts equals hash vec, and then hash vec transform doc, and then I'll have my word counts, and that's a sparse matrix. So I'll go to array. Okay, beautiful. And then I will do data frame equals PD data frame word counts to array. And then we'll look at the data frame here. Okay, now, actually, let's make this 15 features just so it's a little bit easier to watch. Good. All right, so now what I have is, well, what do I have here? What differences do you see between the feature matrix that we created using the count vectorizer and the feature matrix we created using the hashing vectorizer? So one thing is it says floats. So Job was saying it's floats. Sure, we see float numbers here. So we know it's not looking for the count. What other differences do you see? And Florence saying, what is 0 to 14? That's a good question. What is 0 to 14? Does anyone have any ideas? And it also has a lot of zeros. Muhammad is absolutely right. Paul says that they're very happy to be alive today. It's an amazing time to be alive. We have hashing vectorizers. So let's just jog our memory back to Unit 1. Let's go back in time and let's remember what a hashing function is. A hashing function is you have some sort of information. In this case, let's say we have a word, and you put it through your hash function, and what you get out is an integer, and that integer will tell you where to store your whatever came out of your hashing transformation. So if I put something into my hash function, and as an output, I get the number 2, that means that I need to take my input, and I'll store it here. I'll have to rotate it. Actually, I can't rotate it. I'll have to put it into my number 2 box. So hashing always starts with a determined number of boxes in which to store information. It takes the information as it comes in, put it through some sorts of transformation, and then using that information that comes out of the transformation, it stores it in a particular box. And so what's happening here, these aren't word counts at all. In fact, we can do this ourselves in Python because Python has a hash function. We can say best, as in the best of times. We get some sort of crazy number here. And then maybe what I could do is I could divide this by modulo 30. Oh, whoops. And I'll get 13. So I know that if best comes into my hashing vectorizer, I should store it in box 13. If worst comes in, I should store it in box 18. Here we don't have a box 18, but just for example. Oh, whoops, sorry guys. I wasn't showing my screen. So for example, if here I have best, if I have best and I do hash, it gives me some random number essentially. And I can do modular division. I could divide it by 30 and I get 13. So what I can do is I can take my value and I can hide it or I can store it here in the 13th feature. If I have I can store it in the 21st feature. In this case, we don't have a 21st feature, so it doesn't matter. But that's what's happening is the information is coming in, the text is coming in, and it's converting it to some sort of numerical representation that it's then doing modular division on, and then it's storing that information in one of the feature bins that it's created. Now, Stefan has asked, what does number of features mean? Well, the number of features is the number of boxes or number of features you want to store each document in. And if we look at the default for a hashing vectorizer, the default is actually 2 to the 20th power. So it's these huge arrays. And I could make this 15, I could make it 30. I would then get a much wider data frame. But that's okay. And so what's happening with the hashing vectorizer is it is transforming the numbers, transforming the words into these point values, and it's going to store those values in a feature matrix, which might be 15 wide, it might be several million wide. Now, Florin says, should we avoid having so many zeros? No, it doesn't matter. It doesn't matter at all. But one thing that's important to notice is that here, we have no idea what these features actually stand for. I don't know what feature 2 is. I don't know what feature 6 is. I can see that both documents have some overlap in feature 6 and in feature 21, and I guess that's not surprising to me because there's a lot of overlap in these sentences. There's only one word difference, so it makes sense that they would be similar, but how they're similar, how this is being interpreted by our hashing vectorizer, I do not know. It's impossible to know. And somebody was asking yesterday, what's the difference between a stateful and a stateless transformer? Well, if I was looking at word counts, my word counts from Beau to Vec, Well, on the one hand, I can have the array. er, I can see the array here, and I can also see the vocabulary here. Oh, not vocabulary. What is the word I'm looking for? Yeah, it's vocabulary. That's very odd. Oh, excuse me. I need to look at BOVEC. Excuse me. BOVEC vocabulary. I can see that there is a mapping between the words and the features in my transformed feature matrix. So I can look at word counts. Why? Why? There we go. And I can see, okay, best is associated with the 0 column. Of is associated with the or it is associated with the first column, and so on and so forth. So my count vectorizer is stateful. It depends on the vocabulary that's being put into it, and I can also sort of map it backwards and go from features back to original words. So it is stateful. However, if I look at my feature matrix, here I'll put 15 again just to make it smaller so it fits on the screen. If I look at my hashing vectorizer, I can see the array, but what I can't do is look at the vocabulary. In fact, if I type this in, it'll go, I'm sorry, there is no attribute called vocabulary because hashing doesn't work backwards. You can't undo a hash. And that's why we use hashing for creating passwords, for encryption, et cetera, because you can't backwards engineer it. So a hashing vectorizer is stateless, stateless. It doesn't depend on the vocabulary coming in. If I say 15 features, it'll have 15 features. It doesn't matter what the text is. And I also can't go back. And so that's why a hashing vectorizer is stateless. And Florin is asking, where is the meaning of the words defined? And the answer is nowhere. Nowhere here are the meanings of the words defined. Meaning, as we think about it as humans, for the purposes of these models, is meaningless. It doesn't matter whether best, it doesn't matter what best means. It doesn't matter what times means. It just matters that it appears or doesn't in a text. Well, Florin has, so I think Aaron and Florin both have questions that relate to each other. Aaron is asking, what is the real life application of this model? And Florin's asking, what's the difference between pointless and meaningless? Well, this exercise is definitely not pointless. That is, it has a purpose because any text you deal with, you're going to need to turn it into numbers in order for your model to be able to work. So the real life application of this is some sort of vectorizer will always be used, and it underlies all of the models that you will see in the NLP part of this course. In other words, if I go to my whiteboard, our workflow is going to be the following. We're going to have our corpus, and our corpus is going to go through some sort of vectorizer, which is a transformer. And then once it's come through the vectorizer, it'll be a numerical feature matrix that we can use. And then we will pass that transformed feature matrix into our predictor. And we'll put our vectorizer together with our predictor in a pipeline. Now, Jean has a question as to whether you can one column in a data frame be vectorized and be stored in one column? I'm not quite sure I understand that question. Maybe you could rephrase it? So Joebo has one answer. It could be sentiment analysis. That's true. Let's take a look at the mini project, the NLP mini project, and let's just take a look at it. We don't really have enough time to start, but in this project, we're looking at product reviews from Amazon. And what we're going to try to do is, based on the product reviews, the text, the natural language, we're going to build a predictor that's going to say whether it's a 1, 2, 3, 4, or 5-star review. And if I look at the reviews here, so if I look at the data, I see the data type is a list, and I see that if I look at the first item in the list, it's a dictionary. And if I look at the dictionary keys, keys, I can see that there's a reviewer ID, there's a reviewer text, and there's an overall. So if I look at the overall, I can see that I have their star rating. And if I look at review text, I'll probably get something longer. This is some sort of review about buying a mouse. And the question is, can I turn this text into some way of some sort of feature so that I'll be able to predict the number of stars? And I love that people are coming up with other ways to do this. This is just the nature of this problem. So anyways, to pull out the ratings, I'm just going to go uh, D for dictionary, uh, overall for D in data. That'll give me all the ratings. And then what I'll need to do is I'll need to create a bag of words model. And my bag of words model is going to be, and we won't go into exactly how we'll do this. We'll talk about this later. But one thing I'm definitely going to do is I'm going to go from sklearn feature extraction text, whoops, text import count vectorizer from sklearn dot pipeline import pipeline. And I know that my bag of words model is going to be some sort of pipeline. And I know it's going to, well, the first thing is I'm going to need to get reviews. So I'll call this my reviews selector. We'll talk about that later. And I know that I'm going to need to have some sort of vectorizer as an intermediate step. And so I know I'll have my count vectorizer here. And then finally, I'm going to have some sort of regressor. And we haven't decided what that regressor will be. But for example, it could be linear regression here. So what is the practical use of this? Well, we'll see as we move through this mini project together. But any sort of vectorizing needs to happen in your natural learning, in your NLP models. So it's going to underlie all of what you do in natural language processing. And we can talk more about spacey and those other things later. For now, what I really want to drive in here is that a lot of what natural language processing is how do you turn text into numbers? And it could be keeping stop words or removing stop words, doing lemmatization or not doing lemmatization. Um, but it's all going to have some sort of, I'm either turning it into numbers using some sort of count vectorizer or some sort of hashing vectorizer. I see now Joan has a final question. So this will be my final question before I sign off for today. But Jean's question is, if I have a column with text, can I vectorize that text and then store it as a single column in the same data frame without turning it into an array? Not, I mean, I suppose there's a way to do it, but I don't see why you would do it that way. I suppose if I did a hashing vectorizer, no, well, no, I don't think there is a way to do it. You could come up with some sort of hashing system that turned it into a string of into a single number, and you could store that number in the array, or you could store it as a dictionary, and that could be a single that could all fit in a column. But the whole point of this is how do I turn text into a multi-featured array? Okay, everyone. Well, this is it for today. It looks like we are out of time. Florin has a question, which is, am I asking too many questions? The answer is no. You can never ask too many questions in this course. So I really appreciate all of you guys showing up and helping me with your ideas and asking me your questions. And I hope that as we move into more natural language processing, this vectorizing process and all of the other things we learn about will become clearer to you. So thank you so much for attending, and I will see you all tomorrow. And until we meet again, may your data sets be clean, may your models train quickly, and happy, happy, happy data science. Bye, guys. Take care.